Hello, everybody, and welcome back to the second part of the first chapter dealing with sensors. In the first part, actually, we were considering the general conventional environmental sensors. We go in depth with the thermoelectrical sensors, either as a semiconductor material or actually a semiconductor junction, or from a circuit perspective concerning the CMOS technology. Today, or in this lecture, we are going to consider another perspective of sensing unit. Here we are going to discuss together the possibility of using field effect transistor as a sensor, with a given example on some biomedical application where field effect transistor, or typically organic field effect transistor, abbreviated by OFET, can be used in sensing applications. So let's now start by sharing screen, showing our lecture. So I think you can now see my presentation slides, and we can start with FET, or field effect transistor sensing mechanism, with in-depth on nanoscale biosensing. Okay, let's start. So before going generally into FET, let's start with the most common transistor used, or maybe the most common transistor you learned about in your undergraduate study, which is a metal oxide semiconductor field effect transistor, or MOSFET. If you remember, my dear students, MOSFET is a four-terminal device. Source, drain, and gate with the body are the four terminals constructing the MOSFET. Here we have both source and drain with certain type of doping. For example, in this case, it's an N doping. And we have the P channel, or the B region, separating the source and the drain just below the oxide and the gate contact. And of course, this is the substrate connected with the body terminal. Generally speaking, under thermodynamic equilibrium, carriers are not capable of being transferred or transported from the source to the drain, or vice versa. This is simply because of the p-n junction occurs either between the source and the substrate, or between the drain and the substrate. And you can see it here in the energy band diagram, where this barrier, the built-in default potential barrier in a p-n junction, will obstacle the carriers. Here, of course, carriers are electron in the majority region in both the source and the drain to pass either in this side or in this side. So in order to make a connection, in order to make a link between the source and the drain, first of all, you have to get rid out of this barrier. And in order to get rid out of this barrier, simply you have to convert, or to invert this region from being a p-type to be an n-type. To do so, you have to insert some sort of voltage here. This voltage should be a positive voltage. So whenever you have a positive voltage here on the gate, this positive voltage is going to repel the holes here and attract some electrons here to start to construct a link between the source and the drain. The voltage applied here, the positive voltage applied here, we call it the threshold voltage. Threshold voltage is the minimum voltage needed to make this inversion layer, which we call it channel, linking between the source and the drain. So this is the first step toward an operation, or a current transport in a MOSFET, to have a gate voltage sufficient enough to construct this channel, which is called the threshold voltage. Afterward, we go to the next step. Now, after making this channel connecting the both islands, the source and the drain island, still carriers will not go, because simply there is no motivation for these carriers to go from the source to the drain, or vice versa. So in order to bias the carriers, here we are considering electrons. In order to bias electrons to move, then you have to add a source of motivation, which is this positive voltage here on the drain. Once you start to put this positive voltage on the drain, then electrons will start to move from the source through the channel to the drain. Again, remember our previous lecture, free carriers moving then you have a current. The higher the voltage applied to the drain, which is the VDS, the higher the carrier motion in terms of velocity and quantity, which results in a higher current. So this is the first process of operation in a MOSFET. However, after increasing this positive voltage to some sort of a higher voltage level, the probability of finding electron here starts to decrease with respect to here, because simply here the attraction force is very large, just near to the drain, while close to the source, the attraction force is relatively weak. So the channel starts to be reformed in this shape. A narrow channel close to the drain, a wider channel close to the source. The higher the voltage here, the narrower the channel in this region, just beside the drain region. A very important and a very critical point, when you reach a certain voltage, we call the saturation voltage, VDS sat. When you reach this voltage here on the drain, a pinch off occurs in this point. A pinch off is typically that the width of your channel just after the drain tends to 0. So whenever you reach this, you reach the pinch off. If you increase the voltage greater than this VDS sat, what's happened is the pinch off point starts to move from the right to the left toward the source, and your current start to be clipped because you generate a very high resistance region, or in terms of semiconductor, we can say you establish as a depletion region here just before the drain. So your channel is no longer continuous, it's become somehow discontinued by this pinch-off effect. As a sum up, this is a complete operation. First of all, we don't have a channel. When we apply a voltage on the gate, a channel is created. And then we apply voltage on the drain to attract electron from the source to the drain. After that, when we increase the voltage a little bit till we reach what's called the saturation voltage, a pinch-off occurs just on the border of the drain. Finally, when you increase the voltage greater than VDS sat, the pinch-off point starts to increase. It starts to be shifted towards the source. This is simply the process. This process is expressed in terms of IV characteristics with this general, very famous curve for the IV characteristics of a MOSFET. As you can see, first of all, we have this what we call linear or pride region, where whenever you increase the VDS, the current increase. It's something in the form of a resistance behavior, a straight line linear behavior. Till we reach this saturation point when you start to increase the voltage, the VDS, but still your current is clipped to the situation. Of course, you as an expert in this field know that this is an ideal characteristics for a MOSFET. However, the real characteristics show some output resistance with a slope, as you can see in this graph, where this slope indicates 1 over the output resistance of a MOSFET. I'm just scanning this in a somehow a relatively high-speed manner. This is actually because of the reason. The first that I quite you know that you have already studied that in your electronics course. Maybe you can return to our electronic course, ECE05C, and you can return to know more about that. The second reason is actually that MOSFET is not our target in this lecture. Why the MOSFET is not our target? And let's go to this famous technology. Maybe in the previous lecture, we consider what's called the CMOS technology, or the complementary metal oxide semiconductor field effect technology. The CMOS technology is the technology considering both the N channel and the P channel MOSFET. The one on the left-hand side is typically the same we just scanned a few seconds ago. And this is the complementary device where we have the P regions representing the source and drain, and we have the N region to the substrate, and Here you apply a negative voltage in the gate and so on. This is one of the most, maybe it's the most famous and the most utilized technology for electronics everywhere. But let's now return to the concept of a sensor. A sensor is a device that converts a physical phenomenon into an electrical signal. Perfect. So, in order to make this, you have to have what we can call an interfacing element. An element in your circuit, in your semiconductor device, whatever, that sense this physical phenomenon and convert it into some sort of electrical. For example, in our previous lecture, we considered the temperature, and we found that the temperature has an effect, has a significant effect on in the carrier generation. So when you increase the temperature, the electron hole per generation increase in the form or in the existence of a building potential into the p-n junction, then you have a current. Typically, the same when you consider light. Light is a source of carrier or electron hole per generation. We still have a p-n junction, then we have a current. So this is the linking process to convert either temperature or light intensity into electrical signal. Now, what about MOSFETs? In MOSFETs, we have a very important problem or obstacle that all our critical parameters or interfaces are isolated. For example, you can see here that the channel is a very, very, very critical parameter in MOSFETs. For example, if you change the conductivity of a channel, that's, of course, will affect the current flowing from the source to the drain. Here, the conductivity simply means to increase the number of electrons, and because simply this channel is created when you add a positive charge here and you collect electrons. So if you go from an outside source suddenly and you increase the number of electrons here, so you increase the conductivity of a channel, that's obviously mean you increase the current. But the problem that how to reach this channel? The channel is hidden under the gate metal electrode and the gate oxide. Accordingly, this what we can call architecture or this topology of field effect transistor under the name metal oxide semiconductor field effect transistor or MOSFET is not the most famous topology for sensing. Do we have other topologies? Definitely we have other topologies. One of these most famous topologies are the general topology of thin film transistors, or sometimes we call it the TFET. But just take care because we use the TFET for both tunneling field effect transistor and thin film transistor. So maybe it's better to call it TFT, thin film transistor, rather than to call it TFET. But in all ways, this is thin film technology. Here we have somehow the same process, as you can see. We have a source and a drain. We have a semiconductor. We have a conducting oxide, insulator. We have a channel, and we have a gate. So we have everything typically the same like the MOSFET, but with a different arrangement. What is the advantage of this arrangement? The advantage of this arrangement is that you raise up this semiconductor. So this light blue layer, which now become to be the covering layer of our TFT, is darkly or can be darkly exposed to an external agent or an external effect, which is between quotation, the phenomena we are going to measure, the physical phenomena we are going to measure, or the biomedical action we are going to measure, or whatever. That's why this topology or architecture is widely famous in different sensing applications. This is considered, for example, gas sensors or humidity sensors or biomedical sensors. Realistically, actually, this is not the only topology. We have different topologies for these thin film transistors based on the arrangement of the gate and the source and the drain. So, for example, these are the most famous four topologies. These, for example, we call it bottom gate top contact. The gate is in the bottom, the contact is in the top. This we call it bottom gate bottom contact. This we call it top gate bottom contact, and this we call it top gate top contact. So you can rearrange the structures as you like in terms of the contact of the source and the drain, because these are the main biasing contact, and also the position of the gate either on the top of the layer or on the bottom of your structure. Okay, so this, for example, two different topologies where we have bottom gate top contact topology. The main difference, my dear students, between the one on the left and the one on the right is the nature of the material. And this is actually two big sectors in semiconductors. On the left-hand side, we use the conventional inorganic semiconductor materials. Of course, for inorganic, we have silicon, we have gallium arsenide, we have indium gallium zinc oxide, we have a lot of famous either elemental or compound semiconductor materials. And here you can see this is a typical example for that. On the other hand, on the right-hand side, we use the same architecture, the same structure, but with organic semiconductor materials. Actually, it's not the appropriate time to go into the chemical and the material difference between both organic and inorganic. Maybe this is for other contexts in other courses, for other interests. But I think you have the basic background to understand the difference between organic material from organic components and inorganic materials. And of course, this somehow affects the utilization of the device. For example, whenever you are considering under skin biosensors, for example, maybe it's more recommended to use organic material rather than inorganic. Maybe if you are going to use inorganic, you have to use lead-free materials to avoid toxicity, of course. But maybe this is for other more in-depth study for those who are working in fabricating such sensors. Okay, let's go to the next. So this is one of the, or this is the most famous architecture, which is the top bottom gate top contact architecture. Again, it's important to stress on this topology is highly recommended because you have an interface, a direct interface to the semiconductor material. So your injection most likely will be here in this area, which is directly or which is easily to be interacted, and then you can have some sort of reaction here. So let's go to an example for that. One of the very actually, this structure has been used for many biomedical sensing application, but this is one of the most interesting for me, at least. This is one of the most interesting applications. In this example, actually, the targeted is to measure the lactate as one of the very essential and important medical measurements worldwide. As you can see here, they examine, of course, you can access the paper here using this link. You can access the paper. I think it's a part of a free access paper under the Egyptian the EKP, Egyptian Knowledge Bank. You can access this for free, as well as the reference we used in the previous lecture, I think, for the CMOS technology. Again, this is part of the Springer Nature series book, which is also accessible through the EKP for free. So in this paper, they are examining different lactate concentration. And it seems that by increasing the concentration of the lactate, the current decrease. To understand this as a or from an electrical perspective, I used to correlate or mimic this process as a doping process. So usually in this OFETs for the biomedical application, we are using B-type OFET or B-channel OFET. Because this is simply because in most of the organic semiconductors, the mobility of holes is higher than the mobility of electrons. That's why the B-type OFETs are more famous rather than the N-type OFETs. So now we have this organic layer to represent the active layer. Logically speaking, by increasing the hole mobility, or sorry, by increasing the number of holes, that means that you have higher current and the current should increase. So herein, it seems like this is again some sort of analogy. This is an effective modeling. It's not a real process. It seems like we add an N-type material. So whenever we increase the number of the doping material here, which is here the concentration of the lactate, whenever we increase the concentration of the lactate, that means that we are decreasing the number of holes, because generally speaking, when you have a P-type material and you make an N-doping, that means that the N-doped will combine with some of the P, and that will reduce the total number of P. So whenever you increase the concentration, the doping decrease, and then the conductivity decrease, and then the current decrease. This is how I can understand the process, again, from an electrical perspective. This is, of course, not the correct way from a chemical or from a biomedical perspective, but this is just for giving a focus from an electrical perspective or from an electronic perspective for a biomedical sensing. We can see here the effect, which is very, very, very interesting here, because you have an IV curve varying without varying the biasing condition. Usually, it is very easy for us as an electronic engineer to vary the IV curve. For example, let's go, for example, here in this curve, for example, or this one. Here we have a family of curves. But here simply you have a family of curves because you have variation in the biasing condition. Typically here the gate voltage. You change the gate voltage, that's why the IV curves change. But when you get to this slide, I'm sorry, yeah. When you get to this slide, here you have a variation in the IV characteristics for the same biasing condition. You fix the drain voltage, the source voltage, and the gate voltage, but due to the variation in the concentration of the lactate, this affects the active layer here, and you can see different IV curves for the same biasing condition. And that's why this is the sensing phenomena, to have some sort of a change in your electrical outputs due to some physical or here biomedical change in your input. This is typically what we did in, or what we can conclude as a biomedical sensing process using an OFET transistor. So let's go more and more deeply about or inside the OFET, organic field effect transistor, or maybe generally the FETs, the field effect transistors in general. There are four properties, let me say, which we can consider as the most major or dominating properties to evaluate your field effect transistor. Because here we are from the perspective of the manufacturer, from the perspective of the designer. We are the one who designed the OFET in terms of dimensions, materials, and so on. So how can we evaluate our fabricated OFET, or maybe even our simulated OFET? These are the four main parameters. I think the first one, we already introduced it before, which is the threshold voltage. Again, we have the same definition. This is the minimum voltage to be applied on the gate. so that we can have a connection, or what we can call a channel between the source and the drain. And actually, this is a very debatable parameter. Why this is a debatable parameter? Because your perspective or your target may change, or most likely will change, based on your application. Let me give you two extremistic examples. One example can go with a very general or a very common use of a field effect transistor in any low power operation. In this case, or sorry, in any standard operation. In this case, if you have a very low threshold voltage, for example, 0.1, 0.2, 0.3 voltage as the threshold voltage, this might be very risky because your transistor may be turned on based on any random noise in the signal in the system. If I have an OFET with 0.1 voltage, so it's very easy to be turned on. And that's automatically mean loss in power, loss in operation, loss in everything. Alternatively, when we got to biomedical sensing, and if you remember in my previous lecture, I have told you that usually sensors produce a very low voltage. So in your case, you need to detect, for biomedical, for example, you need to detect the smallest possible variation in your input. For example, let's go here for lactate. Your target or your sensitivity will increase if you are capable to make output a change for the smallest possible change in the input. So you target a minimum threshold voltage if possible. That's why in the publications related to biomedical application, you can see the word ultra low threshold voltage, because in such application, low threshold voltage play an important role. So your design perspective for your OFET may differ based on your application. Or in other words, the OFET suitable for biomedical application will not be suitable for other applications and so on. A second parameter, which is the on-off current ratio, which is again a very important parameter. In the on-off current ratio, we have to introduce some sort of a region, maybe you hear about it in your undergraduate, I'm not sure, which is the sub-threshold region. Generally speaking, we assume ideally that whenever the gate voltage is below the threshold voltage, that means that your transistor is turned off. Even in theoretical electronics, we call it cutoff region. But practically speaking, whenever your voltage or whenever your gate voltage is below threshold voltage, your transistor is not turned off. Actually, it is somehow start to wake up, start operation in some sort of a variation we will talk about later on in the next slide to reach the operation point at the threshold. This performance or this variation we call it the subthreshold region. Of course, this current is very low with respect to the current during the normal operation or after approaching the threshold voltage, but this is still considerable. And that's why in this case, whenever you are considering the subthreshold region, which is the curve in red, you have to make it in log scale. That's why you can see the small variation in the current. Why this is important? This is simply because when we start doing the power management or an energy management for our circuit, we simply assume that when your transistor is off, I mean the voltage is below the threshold voltage, your transistor consumes zero power. But practically this is not correct, because as you can see in this red curve, you still have some sort of current. It's a low current, but it still exists. So simply you have power and you have energy. So generally speaking, you target to have this on-off current ratio tends to infinity. Your target is to have a very high on current and a very low tends to zero of current. But practically there is still off current, and you have to consider. Another parameter is still related to the subthreshold region, which is the subthreshold swing. How your current will behave to reach the operation point, in which variation, in which swing. That's why this swing is directly proportional to the variation in voltage and current. And again, as you can see, this is with a log scale of the current, because the current variation is with jumps in order of magnitude. That's why it's in a log format. So here, this variation express how your off current will move, or maybe you can say in which mathematical time it moves to reach the operation voltage. And by the way, I use this graph from the literature because this is one of the comparisons between FET and MOSFETs. We have another perspective of using MOSFET related to the architecture and the exposure of the semiconductor material and so on. But again, there is also a debate between the MOSFET and the FET in terms of these parameters. And here, one of the variation here, you can see that a higher slope in terms of current, I mean, with respect to voltage, of course, a higher slope, but with a lower current. And here we have a lower slope with a higher current, and this some sort of a trade-off between MOSFET and FET in this subthreshold swing behavior. Finally, what we can call the field effect mobility, and just please take care between to distinguish between the field effect mobility and the material mobility. The material mobility is a material parameter, but here this is a device parameter that expresses to what extent there is a channel mobility in your device. That's why here we use what we call the transition characteristics, which is ID versus VGS. You can see it here in this differentiation. So this is simply if we assume ideally that the ID VGS is a straight line. So this is simply the slope of the straight line. So the higher the slope, the higher the mobility. That means that with a lower gate voltage, you can reach a higher current. For example, by comparing this blue curve with this orange curve. However, there's also a constant of proportionality function in the dimension and the biasing BDS, because here you are using a transparent characteristics, ID versus VGS. So you have to have a fixed BDS for this operation. And also there is a capacitance term here. And also, if you recognize, there is also a capacitance term here. And that's lead us to discuss maybe the last slide in this lecture and in this chapter, actually, which is the capacitance model for a field effect transistor. This is one of the very interesting topics related to field effect transistors and MOSFETs and all these transistor relations. Why this is interesting, or why we have to consider it? Why it's important? Actually, the importance of this capacitance model starts to appear whenever you have a frequency-dependent process. Because as you know, my dear students, capacitance appears with frequency. Whenever you are at zero frequency state, or what we can call a DC operation, you don't need a capacitance. But whenever you have a frequency process, a frequency-dependent process, capacitance appears. For example, let me tell you an example. When we start to measure the characteristics of a MOSFET or a FET, the process starts by scanning this transistor under various biasing conditions. For example, we will fix the VGS and we'll start to scan the VDS. And this scanning is some sort of a frequency signal, because you are changing the signal with
a periodic frequency. Herein, the capacitance effect may play an important role in your IV characteristics behavior. So, generally speaking, we know that a capacitor is a junction or a formation of an insulating layer between two conducting layers. However, this is the ideal shape because when we study p-n junction, we know that in a p-n junction, we have a capacitors. We don't have an insulator, we don't have a conductor, but we have a capacitors because we have a depletion region and we have a two partially conducting, partially semiconducting region. That's why we have a capacitance in the p-n junction, especially when it's in the reverse bias condition. So this can be found in our MOSFETs and in the OFETs. For example, we have already an oxide. Below the oxide, we have a channel. And above the oxide, we have a metal. Then here we have a capacitor. In the left and in the right, we have a p-n junctions because this drain and this source are P, or N, and the substrate is B. Then we have a p-n junction here and p-n junction there. Again, between the channel and the substrate, we have a p-n junction. Between the metal and the semiconductor, we have what's called a metal semiconductor junction with a depletion region with a capacitor. That's why we have all these different capacitance models that, as I mentioned, may influence the operation of your transistor based on the frequency of the operation and based on the condition. For example, if you are working below in the substrate region, that means you don't have this channel. So any capacitance related to the channel will not appear. For example, if we have a drain voltage equals to 0 and a source voltage equal to 0, then you will have these p-n junctions under a thermodynamic equilibrium with a constant depletion region. But if you force any of these two to be a reverse bias, for example, then you should expect a higher depletion region. For example, here, if you add a positive voltage to this N-type drain with a grounded substrate, that means that you force this capacitance or you force this p-n junction to be in the reverse bias, which means that you increase in the depression region. So the existence of these capacitors may differ from one region of operation to another. Actually, it's not an electronics course, so you are not going to go into a deep details on about the capacitance model. I just give you a highlight about the existence of this, what we can call, between quotation, parasitic capacitance associated with your MOSFETs or your FETs. For example, this is a model for a MOSFET, but maybe your homework is to implement a similar model for our OFET using the same topology. For example, here we have a metal semiconductor junction. Here we have a metal semiconductor junction. Here we have an oxide layer between two conductors, and so on. So you can build your capacitance model for your FET or any other of transistors based on this knowledge. I think that's all for chapter 1. Thank you very much for your concentration. In the next session, we will have a practice session in solving some design problem related to thermoelectrical sensors, light sensors, and also thermoelectrical sensors, light sensors, and biomedical OFET sensors. This will not be recorded over YouTube, of course. So it will be some sort of an online on-campus solving session. Then we are going to meet in the next chapter with our course. I think the next chapter will be with energy harvesters, considering different energy harvesters mechanisms. Thank you very much for your concentration and see you next lecture, John.